Fernando, vale, ok, te quitaste el sonido, vale, gracias. Okay, good afternoon to everybody. For us today is a pleasure to introduce or to have the speaker, Ardavan, who is a professor in Oxford. He is a physicist working on correlated electron systems and molecular magnetism, and is the director of the Oxford Center for Advanced Electron Spin Resonance. I repeat, it's a pleasure for us, and that he accepted the invitation of giving us the last seminar of this year of this Quantum Tuesdays. So please, Arzhang.
Thank you, David, and thank you for having me. It's a pleasure to be here as well, although it would be even more of a pleasure to visit you in Spain, and we'll do that in the coming months, no doubt. So today I'm going to tell you the story of our exploration of the subject of electrical control in quantum spins. And I'm going to tell you how we've moved through this subject through the results of a set of papers. First of all, some work we did some years ago now, looking at magnetic defects in zinc oxide. This was an experiment that taught us a great deal, and in particular, it gave us some pointers on how we might be able to exploit the ideas we were seeing there in the scanning tunneling microscope to implement electron spin resonance. And then I'll finish by talking about electric field effects in molecular spin systems, which is actually where I entered the subject of spin resonance in quantum spin systems. I'd like to make a particular shout to Junji Liu and Jacob Mrozek in my group, who are actually working on these experiments at the moment, and some work that's ongoing in progress with Aman, Jose, and Alex from Valencia. So where better to start than with Maxwell's equations? And in particular, what I want to highlight here is the difference between the electric and magnetic divergence equations. The point here is that the electric fields have sources and sinks, whereas we don't have magnetic monopoles, at least in our experimental toolkit in the lab. And this has an important consequence if we try to generate electromagnetic fields for controlling systems in the lab. So, for example, if we want to generate a magnetic field, we have to identify which of Maxwell's magnetic equations has a source term, and it's the curl one. And this is why, if we want to turn on a magnetic field in the lab, we need to generate a current. So we generate a current loop here, and it gives us a magnetic field. In contrast, if we want an electric field, we can do it by introducing electric monopoles on some structure. So here are some gold contacts. If we put a voltage, we get charging of one side versus the other, and an electric field. And what this means in practice for experiments where we're applying electric and magnetic fields is that we have more freedom in designing the geometry of an electric field than a magnetic field. And in particular, it's easier to confine electric fields to small length scales than magnetic fields. So what? Why is that an interesting observation? Well, imagine you were trying to build, for example, an information processor whose units, information carrying elements, are spins. It could be a classical one or a quantum one. And most models of this kind of thing involve an array of spins, as shown here. And what we need to be able to do to operate a machine that's based on this kind of architecture is to manipulate individual spins locally, and also to implement conditional operations between, for example, neighboring spins. And if we can do each of these single spin and two spin conditional operations, we can do a complete set of information processing tasks. What this means, of course, is that if we want to make use of small spins and a very dense set of registers, it means that we have to be able to control the spins either individually or their interactions at a very local level. And the more local we can make our control and our interactions, the smaller we can make the device. So this is where the question arises: can we control spins with electric fields? If we can do it with electric fields, we can do things locally and we can increase the density of our machine. Of course, this is not a new question. People have been asking this in various forms since the beginning of the field of quantum information, and even before that, with the field of multiferroics. And here are just a few examples of what people have explored in the quantum information literature. So if we're asking how we can control spins with electric fields, essentially what we're asking is where in the spin Hamiltonian does an electric field sensitivity appear? And so let's have a look at some terms in a typical spin Hamiltonian and ask exactly that question. So the first term that we usually think about is the Zeeman term, shown here. And this parameter G describes the coupling between a spin S and an applied magnetic field B. And of course, this is the coupling that we usually think of using if we want to control a spin system. Now, G can, in principle, be electric field sensitive, but I'm not going to talk about that in this talk. The first term of interest from my point of view today is the anisotropy term. So the simplest anisotropy term is often labeled with a parameter D. It's associated with a spin operator Sz squared, where Z is an anisotropy axis. And depending on the spin system, a typical origin for this term in the spin Hamiltonian might be a crystal electric field, for example. And so plotted below is the Zeeman spectrum, so the energy of the projections of a spin 1 as a function of magnetic field in the absence of anisotropy. And if we turn on that term D, it introduces a splitting at zero field, hence the name zero field splitting term, lifting the degeneracy between ms is plus or minus 1 and ms equals 0 at zero field. So if D is electric field sensitive, then by changing the electric field, we can change this spectrum to the one with dotted lines here using an electric field. This is the effect that we can have on the spin spectrum using an electric field, as long as D is electric field sensitive. Another term that might exhibit an electric field sensitivity is the hyperfine interaction. And so below, I've plotted the energy levels as a function of magnetic field for the simplest hyperfine coupled spin system, an S equals half, I equals half system, electron and nuclear spin both half. And again, if A, the term, the thing coupling this electron and nuclear spins is electric field sensitive, then we can modulate this spectrum as shown with the dotted lines. So it's instructive here to think about the scale of electric fields that generate these terms in typical spin systems. So crystal electric fields are typically of order 10 to the 9 or 10 to the 10 volts per meter. The electric field that might be relevant in thinking about the hyperfine interaction is perhaps the electric field of the hydrogen nucleus, the proton at a Bohr radius, and that's of order 10 to the 11 volts per meter. So if we want to significantly modulate these terms D and A using an externally applied electric field, we'd better keep in mind the scale of the intrinsic voltage or intrinsic electric fields giving rise to the phenomena. And so the numbers 10 to the 9 and 10 to the 11 look really big. So at first sight, this looks like a difficult problem. But of course, the electric field in a mains electrical supply is of order 10 to the 5 volts per meter, a few hundred volts over a millimeter or a fraction of a millimeter. And so although these intrinsic electric field scales are high, they're not completely beyond imagination that we can modify these terms. So if we do have an electric field sensitive spin Hamiltonian, how are we going to measure it? What kind of experiment can we do to actually probe the sensitivity? Well, a classic way of looking at spin Hamiltonians is via electron spin resonance. And the simplest experiment of this kind is a continuous wave experiment where we apply microwaves at some frequency, nu, and we sweep the magnetic field. And at the point where the microwave frequency matches the energy difference of delta ms equals plus or minus 1 transitions, we can see an absorption of the microwave signal. So for that spin 1 system that I showed you earlier, without any anisotropy, there are 2 degenerate transitions that appear at the same magnetic field. If we turn on the anisotropy, then we see transitions at that resonant frequency at 2 different magnetic fields. We see a splitting of the ESR spectrum. We see absorption at 2 values of the magnetic field here and here. So what happens if our anisotropy parameter D is electric field sensitive? Well, we see that we can shift the resonance position in magnetic field by shifting the magnitude of the zero field splitting. And so if D is electric field sensitive, we'll see a shift of the ESR lines as a function of magnetic fields when we turn on the electric field. So this is, in principle, how we might measure it. There's a problem with this kind of experiment. It can be done in certain systems, but there is a problem with this approach on the whole, which is that very often the inhomogeneous broadening of these transitions is such that the shift that you can generate using an electric field is too small to be able to resolve the shift caused by the electric field. So the line widths are broader than the shifts that we measure typically. And so in certain systems, we can do an experiment that is rather more sensitive based on probing the phase of a quantum superposition of the spin levels involved. And so this is what's called the Hahn echo sequence. It's a standard building block of time-resolved magnetic resonance experiments, both electron spin resonance and nuclear spin resonance. And what we do at time 0 is to apply a short pulse of microwave radiation such that we set up a coherent superposition of the 2 spin states involved in our transition. And since there's an energy difference there, that superposition accumulates a phase coherently as a function of time. But the inhomogeneity in the system means that the transverse magnetization in this example decays as a function of time. The inhomogeneity and the energy difference means that the precession rates, or the rates at which superpositions across an ensemble accumulate a phase, go out of phase. And so we lose the transverse magnetization. But as long as that inhomogeneity is static, it is refocused. If we introduce a pi pulse at some time here, it essentially inverts the time evolution of the system, and the system can come back into phase after another period of free evolution to form what's called a spin echo. Now, the Hahn echo is interesting in the context of the electric field experiments, because if we were to introduce a perturbation during one of the periods of free evolution of the system, as long as that perturbation changes the energy levels, the energy difference between the levels supporting the superposition, we accumulate a phase during the application of the perturbation. And that phase is reflected in the phase of the echo that we receive. And so because this is an experiment that is sensitive to the quantum phase of the system, it can be much, much more sensitive than in the continuous wave experiment I described a moment ago. So most of what I will show you today is based on this Hahn echo sequence. Before I show you some data, I would just like to note a few points about how we do the experiment. First of all, let's look at the role of inversion symmetry. If we imagine spin centers of various kinds, and in particular, if we compare spin centers that are inversion symmetric with those that are inversion symmetry breaking, we can see that an inversion symmetric center is not allowed to have a first order response to the electric field, because the electric field pointing this way has the same effect as an electric field pointing in exactly the opposite direction. And that means that inversion symmetric spin centers have a leading dependence as E squared. There's no linear electric field effect for an inversion symmetric spin center. In contrast, if inversion symmetry is broken, a field pointing one way looks different from a field pointing the other way, and that system can have a linear response to the electric field. So how can we do an experiment to separate the linear from the quadratic sensitivities in electric field? Well, the plot above is the experiment I just described. We apply an electric field for some duration of the free evolution in a Hahn echo sequence. And if we compare that with applying a bipolar electric field pulse, so an electric field, a positive electric field followed by a negative electric field of the same duration, if the response of the system is linear in electric field, we'll accumulate a phase here. But in this case, the phase that's accumulated here will be cancelled by the phase that's accumulated there. And so a linear sensitive system will have no effect from this sequence. But if the sensitivity is quadratic, then the sign of the electric field is not important. And so we'll see the same phase shift for this sequence as for this one. And this is the most elegant way to distinguish a linear from a quadratic electric field sensitivity. But it does demand that you can apply bipolar electric field pulses, which can be challenging technically, and it's certainly more expensive than applying electric fields of single polarity. So another approach to this question is to vary the area of an electric field pulse. So here I have plotted an electric field pulse of a long duration at a small amplitude, and here an electric field pulse of half the duration and double the amplitude. If the response of the system is linear in electric field, then the effects of these two pulses will be the same. But if it's quadratic, the effect of this pulse will be larger. And so there are various ways that we can distinguish linear and quadratic electric field effects. Okay, so I hope that motivates why the question of electric field effects in spin systems is interesting, and a brief overview of how to measure it. So let me go on and show you some data. So we actually started looking at magnetic defects in zinc oxide because zinc oxide is quite an interesting material. It's a wide bandgap semiconductor. And crucially for our purposes at the time, it has a low abundance of magnetic nuclei. Now that's interesting because magnetic nuclei, the fluctuations associated with the magnetic field when in the presence of magnetic nuclei is one of the key reasons that spins, electronic spins, decohere in these kinds of systems. And so if you can find a host material with a low abundance of magnetic nuclei, you can expect longer spin coherence times. So that was the original motivation for looking at zinc oxide. Others find other reasons for investigating it. It's considered these days as a technological material. In particular, it's a piezoelectric. So it has a spontaneous inversion symmetry breaking in its crystal structure, which means it has an internal polarization, and that gives rise to piezoelectricity. So manganese 2+ is a common impurity. Even if you try to buy nominally pure crystals of zinc oxide, very often there is some manganese impurity in there. And it sits on the zinc site, and it has a spin of 5 halves with a small axial anisotropy and a nuclear spin, of 5 halves as well. So that gives rise to ESR transitions, as shown here. So the spin Hamiltonian is very simple. It has, to a good approximation, an isotropic G factor, this simple axial zero field splitting term, and an approximately isotropic hyperfine interaction. So the spin spectrum is shown here. There are 5 electron spin resonance transitions shown in different colors. And shown below is effectively the ESR absorption spectrum in a real sample. So this is real data. You see a very beautiful spectrum of 5 groups of lines, each split into 6 by the hyperfine interaction with the S = 5 nucleus. So from this spectrum, we can measure the scale of the anisotropy energy and the hyperfine interaction. And sure enough, at low temperatures, the spin lifetimes are incredibly long. So the phase coherence time for these spin superpositions is on the scale of a millisecond, and the longitudinal relaxation time, the energy relaxation time T1, is in the seconds at low temperatures, inconveniently long for doing experiments. So what happens in this system when we do the electric field experiment? Well, what's plotted here is the spin echo, real and imaginary parts in red and green respectively, as a function of the area of the electric field pulse applied during the first period of free evolution in the Hahn echo. So there's quite a lot going on here, and I'll explain it piece by piece. So what we're doing here is we're applying the magnetic field along the anisotropy axis. So SZ is a good quantum number. And we're applying the electric field parallel to that too. That is also the piezoelectric axis of the zinc oxide. So if we look first at the half-half transition, let's just go back to see where that is on the spectrum. That's this transition here between the ms = -half and ms = +half levels. If we trace those back to 0 magnetic field, we see that those 2 levels are degenerate even with the 0 field splitting present. And so if we modulate D, we don't expect any shift in the transition energy for this transition. And sure enough, that's what we see. So as a function of the electric field, very little happens to the spin echo formed on a half-half transition. But in contrast, the half-3-half superpositions and the 3/2, 5/2 superpositions show a very strong sensitivity. And in fact, the effect of this electric field pulse is to coherently rotate the superposition as a function of the duration of the pulse. So this oscillation we see is a coherent phase gate, effectively, on the two levels, half, three half. And the origin of this, there's a smoking gun for the origin of this, because we can see that the frequency or the period of the oscillation for the half, three half transition is a half of that associated with the 5 halves, 3 halves transition. And the reason for that is that if we again go back to the spectrum, if we shift D, the gap between a half and 3 halves is half of the size of the gap between 3 halves and 5 halves. And so the sensitivity of the coherence is doubled for the 3 halves, 5 halves coherence as compared to the 1 half, 3 half coherence. So this really tells us directly what the origin of this electric field effect is, and from it we can extract how sensitive that anisotropy term D is to the electric field we apply. D is made up of a component that's there in the absence of the electric field, presumably due to the spontaneous internal distortion in zinc oxide, the natural electric field it sees, and some term that is proportional to the electric field that we apply with a constant K that we can back out from this experiment. If D is in frequency units, it's 3.3 hertz per volt per meter of electric field that we apply. So this shows us that we can manipulate the state of a superposition between two spin SZ levels that we introduce using a microwave pi/2 pulse. But it also gives us a tool for actually driving the spin system with an electric field alone. And so let's have a look how that works. So the experiment I've just described to you, the electron spin resonance, the traditional electron spin resonance experiment, we apply a large magnetic field along Z so that eigenstates of SZ are, the states of SZ are the eigenstates of the system. And then the microwave field that we apply introduces a magnetic field in the transverse direction, SX, that is modulated. And so when the frequency of the modulation of the transverse field matches a delta ms equals plus or minus 1 transition, because SX has terms S plus and S minus, we can drive transitions between those states. Now, what we have in our system is an alternative perturbation that we can modulate with a time-dependent electric field. So instead of our transverse term being Sx, if we were to apply the magnetic field at some angle theta to the anisotropy axis, as long as the magnetic field is, the Zeeman energy is large compared to the anisotropy energy, we can write we can consider the eigenstates of the system still to be states of Sz. And then the anisotropy term becomes the square of a linear combination of Sz and a transverse term. And so multiplying that out, we find that we have terms in this anisotropy energy that look like Sx squared and terms that are linear in Sx. And so if we modulate its amplitude with the electric field, this perturbation can actually drive transitions both delta ms equals plus or minus 1 or plus or minus 2, depending on the orientation of the magnetic field with respect to the anisotropy axis. And so we can, in principle, drive the system, and in fact, we can drive a richer set of transitions with this anisotropy term than we can with a transverse magnetic field. So we did that experiment. We tried it in the manganese and zinc oxide. We used a rectangular resonator in a TE102 mode, and we put the sample in an electric field antinode here. And we looked at the transitions as measured from the absorption of the in the resonator as a function of the orientation of the static magnetic field with respect to the microwave electric field. And so here we can see transitions that are spin transitions, but driven by an electric field. So they're electric dipole spin transitions in this manganese and zinc oxide system. So this experiment from some years ago now really taught us quite a lot of lessons. We understood that a high spin system can have an anisotropy energy that is in principle sensitive to an external electric field that we can apply. We can coherently control superpositions between spin states using electric field pulses. And in principle, we can drive transitions also using a high frequency electric field. And at the time that we were doing these experiments, I was collaborating with Andreas Heinrich's group at IBM Almaden, and they were doing some very interesting experiments probing quantum spins on surfaces in the STM using various techniques. And we set ourselves the question of whether we could do electron spin resonance. And actually, it turns out that things we learned from the manganese experiment were very useful in that program. So here is what the STM people were doing with spins on surfaces at the time. So here's my schematic of the STM. We have a tip, a metallic tip and a metallic surface. And the experiment comprised a single magnetic atom sitting on top of some kind of insulating layer, which decoupled the magnetic atom from the metallic substrate. And one of the key experimental techniques one has in the STM is the measurement of inelastic tunneling spectroscopy. So the experiment here is to look at the tunnel current between the tip and the surface as a function of the voltage applied between the tip and the surface. And if tunneling electrons have enough energy to generate some kind of excitation in the system sitting on the surface, then they have several ways of getting through the system. So a Fermi's golden rule argument tells you that you expect a larger conductivity when the voltage exceeds the energy for some internal excitation of this system on the surface. So as a function of the voltage you apply, you see steps in the effective conductivity, dI by dV. And if those internal excitations are spin excitations, this gives you a way of doing spectroscopy of the spin transitions. And so as a function of the applied magnetic field, you can see these steps in dI dV move around and extract from that the terms in the spin Hamiltonian for this spin on the surface. Another beautiful ingredient that you can introduce in this kind of experiment is to make the tip magnetic. So you can pick up a collection of magnetic atoms on the tip, and then you have a tunnel magnetoresistance between the tip and the surface atom. So depending on the relative orientation of the magnetization of the tip with respect to the surface atom, you can see a difference in the conductivity. And so this gives a new set of mechanisms for probing the magnetization of the spin on the surface. And the IBM group developed some very beautiful techniques for doing pump probe spectroscopy by introducing time dependence on the voltage on the tip, so the voltage pulse to randomize the surface state spin, followed by a small voltage pulse to measure the relative orientations. They were able to look at relaxation times, T1 times, for spins on the surface. But all these techniques are limited in energy resolution by the fact that there is a Fermi function governing the population of states in both the tip and the surface. And so the limit to the energy resolution is actually some kind of convolution of two Fermi functions, and it comes out at a bit over 3 times kBT. T is the temperature of the system. And so the question we asked ourselves was whether we can think of how to do electron spin resonance on this atom on the surface, because then we might be able to do to get a higher energy resolution for the spin states. The big problem here is how to plumb in a magnetic microwave field to generate the spin transition. So we have a set of metallic pieces of the system around here, and it's quite difficult to work out how to introduce enough magnetic field to get transitions. But of course, what you have in the STM is a voltage between the tip and the surface and a very, very small distance. This distance is typically less than a nanometer. And that means that the intrinsic electric fields in this system are very large, and you get them for free. And so the question is, can we learn from the manganese in zinc oxide experiment to see how to use that electric field and a time dependence on that electric field to drive spin transitions for the atom on the surface? And of course, the answer is you can do it. The first system that the STM people managed to do it on was this iron on an MgO surface. And this was a system that was studied quite extensively using the inelastic tunneling spectroscopy and bulk or surface science techniques like XMCD, X-ray circular dichroism. And so its spin Hamiltonian was quite well known already. It has an orbital moment of 2, a spin of 2, an axial anisotropy associated with LZ, some spin orbit coupling, some Zeeman interaction with an external applied electric field, and this 4-fold anisotropy energy in the plane associated with the 4-fold site that the ion sits on the MgO surface. So the axial anisotropy is quite big. This 4-fold anisotropy is really quite small. But knowing this spin Hamiltonian, we can work out what the ground state energy levels are. In the absence of a magnetic field, of course, they're degenerate, but with an electric field, with a magnetic field applied perpendicular to the surface, we can lift the degeneracy between these two states. It turns out we also need some in-plane component to mix the spin part of the wave function. But if we have those two magnetic fields, static fields present, then modulating the tip voltage modulates this parameter F0, which in turn modulates the amplitude of the operators L plus to the 4 and L minus to the 4, which is enough to mix these states of LZ equals plus and minus 2. And so you can drive, using a resonant tip voltage, you can drive transitions between these two states. And so here is the first ESR STM experiment of that kind. You can see, so the tip, it was a magnetic tip, which gives some contrast in the current when you change the spin state of the surface atom. And so as a function of the applied frequency here, you can see a peak in that tunnel current, which depends on the magnetic field that's applied on the Zeeman energy, effectively. And so this is electron spin resonance of that single atom on the surface in the STM. Just as a demonstration that you get very high energy resolution, iron appears with various isotopes. Iron 56 is a spin 0 nucleus, iron 57 is a spin half nucleus. And if you look very closely at these ESR transitions, you can see the splitting associated with the hyperfine interaction in iron 57. And the energy resolution is a few hundred megahertz. It's a very small energy in comparison with the energy resolution when it's limited by the Fermi functions between the tip and the surface. Of course, what we did in that experiment was to identify one mechanism by which a modulated tip voltage can drive a spin transition. And once you actually start doing these experiments, it emerges that there are a range of other phenomena that could be important. And so as an example that Joaquin Fernandez-Rossier's group identified and described in some detail is that when you have this tip close enough to the surface atom to have a tunneling current between them, you also naturally have an exchange interaction between them. And the effect then of modulating the tip voltage is to modulate this, this spatial separation, and therefore also to modulate the exchange interaction. And that appears as an effective magnetic field modulation on the surface spin, and that too can drive a spin resonance. So it turns out actually that this electric field modulation can give rise, can be used in quite a wide range of surface spins to generate electron spin resonance. And there are various experiments you can do to distinguish which mechanism is at play. But just to show you that it works in other systems and that you can do coherent manipulations of a spin, these are Rabi oscillations of a surface titanium spin on an MgO surface. So what you can see here is the coherent oscillation of the surface spin state as a function of the duration of an electric field pulse, a microwave electric field pulse on the tip. So the scanning tunneling microscope ESR field is moving at pace, and it's very exciting because it gives us a way of doing highly controlled, highly reproducible manipulations using ESR of individual quantum spins on surfaces. So that's the STM story. I'd like to finish by talking a bit about the molecular spin systems, which is where I mentioned at the beginning, I got into the coherent spin physics game. And it turns out that if you want to do experiments, electric field effect experiments on these kinds of systems, there are some subtleties that you have to take into account. So let me introduce the kinds of systems we're looking at here. We're interested in molecular magnets, and typically these are clusters of, for example, transition metal ions, which have strong exchange couplings and can be described by some effective low energy Hamiltonian, typically with a Zeeman term and various anisotropy terms. And here are two examples of the classic molecular magnets, iron 8 and manganese 12. And the reason that people are interested in these kinds of things is that molecules are engineerable in ways that, for example, atomic defects in semiconductors and individual atoms on surfaces are not. So one can modify the properties of the spin system with some rational chemical design of the environment for this cluster of transition metals. And so there's promise for engineerable quantum magnetic systems. And so the same question is interesting. Can we, in these molecular magnetic systems, control this effective low energy spin Hamiltonian using electric fields? And the first insight on this question was offered by the group of Daniel Loss in some important papers around 2008. And they considered perhaps the simplest example of an exchange coupled system, a triangle of spins a half. Oh, the Hamiltonian just arrived. So this system has 3 spins, S1, S2, and S3, all coupled through an exchange interaction. And if the sign of J is positive, if we set one of the spins down, its neighbor wants to be up, but the third spin then cannot satisfy the exchange interaction for both of these bonds. You can't have the minimum energy for this bond and this bond at the same time. This is known as magnetic frustration. So this is an interesting theoretical system, and it shows up in some practical examples too. The eigenstates of this system are made up of two manifolds. There's the high energy manifold where the three spins are aligned and there's a maximum energy cost from the exchange interaction. But the ground state, so that's S equals 3/2 and takes up 4 states. Because we have 3 spins a half, we know that the lower energy manifold should also have 4 states. 2 of them, or half, are offered by the fact that the total spin is a half, and so we have 2 projections of that, ms equals plus and minus a half. And the other 2 states are accounted for by considering a chirality of the superposition of 2 spins up and 1 spin down. And so this chirality quantum number takes 2 values, plus or minus, as shown here, and can also be considered as a possible degree of freedom for use as a qubit. But this picture is instructive in understanding what happens when we apply an electric field. So if we apply the electric field, in a real molecule, there will be some kind of charge disproportionation, and the effect of the electric field will be to distort the molecule. And when we distort the equilateral triangle into an isosceles triangle, the effect of that will be to lift the degeneracy between the 3 exchange interactions and introduce a difference between what I've labeled J prime and J. And this, of course, lifts the chiral symmetry of the system. And so we can see immediately that chirality will no longer be a good quantum number. And so that 4-fold ground state must split by an amount that will be characterized by the difference between the 2 exchange interactions. And there are some interesting details in this, but the crucial observation is that in this exchange coupled system, the natural effect of an electric field is to modify the spin Hamiltonian, which at first sight is not a trivial observation. So if you actually want to do this kind of experiment, there are some interesting experimental challenges. And the key one arises because typically a crystal of magnetic molecules, here's an example of a copper 3 triangle, which is a real example of the triangle of spins a half. If you grow a crystal of this, then these molecules are separated by a length scale of order a nanometer, and the through space dipolar interaction between the magnetic elements within this crystal means that the phase relaxation time for the spins is very short. And so if you try to do a Hahn echo experiment on a crystal of these molecules, generally the relaxation time is too fast, too short to be able to see an echo at all. And so what we do in these experiments is dissolve them in some suitable solvent so that we can increase their spatial separation, reduce the dipolar interaction, and then we can see Hahn echoes. The downside of dissolving molecules is that we lose the orientational order. And so within the ensemble that we're measuring, we have molecules at all orientations. So to understand the effect of that, let's take this molecule, which is oriented in a particular way. And if we do a Hahn echo on it, we see the echo form in some direction in the XY plane. Now, if we apply an electric field to this system, and there is an electric field sensitivity, as I explained earlier, the effect of the electric field pulse is to introduce a phase on the echo. And so the phase appears at some different place in the XY plane. But since we're looking at a disoriented ensemble system, for every molecule that has this orientation, there is its inversion-related cousin, or the molecule pointing in the other direction. And for the same globally applied electric field, here in green, the effect of the electric field on this molecule will be exactly opposite what it was on that molecule. And so we'll shift the phase of the echo in the other direction. And what we measure in the ensemble experiment is the sum of all the echoes from all the molecules. And this argument tells us that in the ensemble experiment, the effect of the electric field will be to decrease the amplitude of the echo, but we must not acquire any phase because the phase associated with this molecule in this direction is exactly minus the phase associated with that one. Now, these are not, of course, the only two orientations for molecules in our system. We have all the other orientations. And so, in fact, across the ensemble, we're going to get a whole set of different phases on our echoes. We're going to have an inhomogeneous distribution of phases. And there's another effect. It's taking a moment to appear. Okay, here it comes. The way that we apply the electric field in these systems that are dissolved in some solvent is to introduce into the circular test tube, effectively, that's holding the sample, a pair of wires vertically. And when we apply a voltage between these two wires, we get a rather inhomogeneous electric field arising from that. And so there's a finite distribution of electric field strengths and directions associated with this experiment, which introduces yet another inhomogeneity in the system. And so when we do the experiment, when we do the Hahn-Echo experiment, as I described earlier, and increase the duration of an electric field pulse, what we see on the echo amplitude is a decay as a function of the duration of the pulse. But when we extend the electric field pulse past that refocusing echo, the effect of the electric field pulse is like a static inhomogeneity. And as a function of time following, the echo recovers as the electric field pulse extends through the full duration of the Hahn-Echo sequence. And if we see this recovery, that tells us that the effect of the electric field that we're applying is perfectly coherent. It's a refocusable manipulation of the state of the system. So let me briefly show you some results on two classes of molecules. This is the copper-3 molecule that I showed you a moment ago. We also studied a class of molecular magnets called chromium-7m antiferromagnetically coupled rings. These are interesting as a class of exchange-coupled clusters because you have 7 chromium atoms and a heteroatom that you can choose. And choosing nickel, for example, the total spin of the cluster is half. If you choose manganese, the total spin is 1. And you can adjust that heteroatom with minimal changes to the physics of the system, but tuning the spin Hamiltonian in a controlled way. So if we look at the results of the electric field experiment, this is on the chromium-7 manganese. That's an S=1 exchange coupled cluster. And here we're plotting the whole echo plotted vertically as a color plot as a function horizontally of the duration of the electric field pulse. And here you can see that decay of the echo and its recovery, confirming that there is an electric field sensitivity in this molecule and that the electric field is coherently rotating the spin state. And from this dependence, we can extract the sensitivity. It's about 2 radians per second per volts per meter that we apply in the electric field. Just having a look at the comparison between changing the duration of the electric field pulse and changing the amplitude of the electric field pulse. This is the experiment that allows us to distinguish between linear and quadratic effects, we see that we're sensitive only to the area of the pulse, implying that this is a first order effect. And indeed, this is an inversion symmetry broken system, so that's not a surprise. Looking at the spin half analog, we see no effect. And that might imply that in the spin 1 system, what we're modulating with the electric field is the anisotropy energy, but we can't rule out that there is also some modulation of the hyperfine interaction with various magnetic nuclei in the system. And looking at the copper-3 triangle, this is a spin half system, the exchange coupled system. It's a real analog of that frustrated triangle that I showed you earlier. Here we also see a coherent phenomenon with a rather comparable phase shift as a function of the applied electric field. David, I'm conscious of time. How long should I draw to a close now? Or do I have a few more minutes?
Feel free. You have few more minutes. Yeah. So
let me tell you about one more molecular system that we're working on at the moment, which is shows us some interesting phenomena. So these antiferromagnetic rings and the copper-3 are examples of exchange-coupled molecular spin systems. There are also, there's another class of interesting molecular magnetic systems where a single magnetic ion lives in some environment within a molecule and acquires a non-trivial spin Hamiltonian. And one of the beautiful examples of this is a holmium atom in a tungsten cage. And this system has become famous because its ground state with J of plus and minus 4 experiences a fourfold perturbation associated with its local molecular environment, which mixes the plus and minus 4 states to generate clock transitions within the spin Hamiltonian. So as a function of the applied magnetic field, there are regions in the spin spectrum which to first order are insensitive to the applied magnetic field. And transitions at these positions in magnetic field show much less sensitivity to environmental fluctuations of the magnetic field, and therefore longer coherence times than transitions away from this anti-crossing point. And so this was investigated by Steve Hill's group on molecules grown in Valencia in this important paper from a few years ago. What's interesting from our point of view is that the origin of the Hamiltonian term that generates this clock transition is, as I mentioned, associated with the local environment that the holmium atom sits in. And so it has a fourfold oxygen environment above and below, and these two are rotated with respect to each other. And distortions from 45 degrees or distortions of the location of the holmium between the two plaquettes of oxygen can both contribute to that Hamiltonian term generating the clock transition. And because there are charge imbalances between these units in the molecule, an externally applied electric field can modify both of these parameters in principle. And that means that an externally applied electric field modulates the amplitude of the term generating the clock transition, and therefore the amplitude or the frequency of the clock transition itself. And this is a nice molecular system because we can dilute the magnetic holmium tungsten 10 in a diamagnetic host crystal, which has the same morphology. And so we can achieve dilution between magnetic centers without losing orientational order. And so this is the result of that experiment, which is by now familiar. We apply the electric field as a function of duration of the electric field. We can see oscillations in the echo that we receive. And in this case, because we have a crystal, it makes sense to look at both the in-phase and quadrature components. Now, there are 2 holmium tungsten 10 molecules per unit cell in each unit cell of the crystal, which are inversion symmetry related. And so, as I described earlier, for a given electric field direction, one of them has its phase accumulating in one direction, the other in the other direction. And so we still expect no quadrature component in the echo, but across the ensemble, the effect of the electric field is homogeneous. And so we see this rather beautiful oscillation. And because the electric field is directly modulating the Hamiltonian term, giving the transition energy that we're looking at, this system is extremely sensitive by comparison with others to the electric field that we apply. And so we see a much larger electric field sensitivity than in the other molecular systems that I showed you. And indeed, this sensitivity is large enough that we can actually tune the ensemble of spins that we're driving in our Hahn echo sequence in and out of resonance of the microwave pulse using an electric field pulse. So here is that Hahn echo sequence. We apply a pi/2 microwave pulse, followed sometime later by a pi pulse. And what we're doing in this experiment is applying an electric field at the same time as the pi pulse. So we're changing the resonant frequency of our spin system using the electric field. And then we can do spectroscopy on that by sweeping the frequency of the refocusing pulse and seeing at what frequencies we do get some refocusing. So down here, you can see the effects of that. We see a splitting in frequency space of the frequencies at which the refocusing pulse is effective as a function of the applied voltage. And the fact that we can see 2 separate echoes as a function of that frequency offset tells us that we can tune our system, the frequency of our transition, by more than the intrinsic line width of the system that we're exciting. And this is quite an important observation, because it means that using an electric field, we can tune molecules in and out of resonance of an applied microwave field using an external electric field. So this is one of the key things that it was interesting to be able to do that I introduced at the very beginning. So this system is actually giving us also quite important insights into exactly what it is that gives us an electric field sensitivity in a molecular system. And what we're learning from that might help us in future to design molecular systems with electric field sensitivities in mind. So to conclude the discussion of molecular systems, there are various reasons, various mechanisms, again, for how an electric field might modulate a molecular magnet moment. And we can actually do experiments as long as we take the particular circumstances into account. And it remains an interesting and open question how to design spin electric couplings in magnetic molecules. You may want molecules that are insensitive to electric field noise, for example, so can remain coherent in the presence of charge fluctuations, or you may want a molecule that has a high sensitivity if you want to be able to use the electric field to manipulate it. So I'll finish by thanking the wide range of people, many groups who have worked with me on these various electric field experiments, from the manganese in zinc oxide, the STM group at Almaden, and now also a group in Seoul, and the theory group in Braga, and the molecular systems, the group here in Oxford, synthetic chemists in Manchester and in Jena and Valencia, and also the theory contributions of Alex Gaita and his collaborators Aman and Jose in Valencia. So thank you very much for your attention.
So thank you very much, Arzhang. So there are quite a few questions. Maybe also Fernando Luis will join later, but let me just read first the questions of the chat, okay?
Good, yes.
So since I'm going to read it. So since the electrical response seems to be highly dependent on the system's spin being greater than 1/2, is there any ab initio method to estimate the coupling strength of the sample?
That's a really important and interesting question, which is at the heart of the final point on the conclusion. Can we understand how to use the various origins of spin electric couplings? So I skirted over the possibility that the G factor can be electric field sensitive at the very beginning. So for a spin half system, if it has a G equals 2 and it's isotropic, it's unlikely that there will be a strong electric field sensitivity. But in many systems where the Zeeman energy is as a result of a combination of contributions to the magnetic moment from the electronic spin and an orbital component, of course, you find G values that differ from 2 and or become anisotropic. And so in spin half systems with anisotropic G factors or G factors different from 2, we can expect an electric field to have more effect. Now we can say directly from symmetry arguments whether we expect its sensitivity to be linear or quadratic. But beyond that, you need, as the questioner suggested, a fairly detailed ab initio model that can take into account the distortion of the system owing to an external electric field. So there, I don't think I have a general answer to that question, but I do think it's an interesting one.
So related to this, I don't know if it is related to this question, but this is mine. So in the figure, one of the last figures that you saw us today about this splitting of the peaks, this was for the clock transitions. Yeah, this one. So what was the intensity of the electric field to observe this?
So we're applying of order 100 volts over a few millimeters. And the interesting parameter for a linear effect is, for a linear effect is the frequency shift divided by the electric field that's applied. And in this case, that's about 70 radians per second per volt per meter. So this is actually comparable with the scale of the effect in manganese in zinc oxide, and more than an order greater than for the exchange coupled systems I showed you earlier. And so the message is that different systems can be sensitive in very different ways. And actually with Alex's group in Valencia, we've been trying to rationalize our understanding of this through a consideration of how the electric field actually distorts the molecule, and then how that distortion feeds into the spin Hamiltonian. And so the normal modes of the system, for example, offer a convenient orthonormal basis for distortions. And they also are an output of DFT packages. And the infrared transition intensity is a measure of the change of electric dipole associated with each of those normal mode distortions. And so actually you have quite a lot of information that lets you try to back out the effect of an applied electric field from these parameters that are derived from ab initio calculations. So we're working on a kind of general approach to trying to understand how an electric field that you apply can modify the spin system. But I think there's huge scope for understanding this better. And there are some very interesting open questions.
So I will try to interpret this question a little bit. So I think because at the beginning of your talk, your motivation is trying to control or to induce also transitions via the electric field, right? So in this, when you saw this linear chain to make just, for example, 1 qubit gates or 2 qubit gates or something like this. So with this, in this discussion, is it possible to compare the strength of this with the electric field and with the magnetic field?
Yes. So, of course, one of the central objectives in quantum spin manipulation games is trying to get strong coupling, for example, between the spin and the control field, whether that's an electric field or a magnetic field. And the fact that the origin of magnetic fields of controllable, switchable magnetic fields in any experimental geometry lies in currents constrains the geometries of magnetic fields that you can design. And so there are various designs that people have proposed for magnetic field resonators with a magnetic field antinode where you can put your spin system that tries to concentrate the magnetic field as far as possible and thereby enhance the coupling as far as possible between the magnetic field and the spin system. The fact that we have the possibility of electric field driven spin transitions poses for us the question, can we design microwave resonators where the electric field antinode is even more confined? And can we, through that, get stronger coupling between the power of microwaves that we put in and the spin system? And the real prize, of course, is to get an appreciable coupling between the microwave field associated with a single microwave photon and the spin system. Now that's some way off. And it remains an open question whether we can design resonators and spin systems where through the electric field coupling, we can get a stronger coupling to the microwave than through the magnetic field. I think there's every prospect of it for the reasons that I already mentioned to do with electric field geometry and the potential for designing large electric field sensitivities into, for example, molecular systems. But I don't have an answer. I can't say yes or no, but perhaps and hopefully.
Okay. So there's another question. I understood that the inversion symmetry in diluted samples of magnetic molecules affects the echo. Does this mean that the diamagnetically diluted crystals with inversion symmetry share the same effect?
Yes. So, so the holmium tungsten 10 example is educational from this point of view as well. Well, let me show you the result of the experiment. So each molecule in this crystal is itself inversion symmetry broken, but each unit cell in the crystal has 2 molecules which are inversion symmetry related. So the ensemble that we measure has half the spins pointing one way and half the spins pointing exactly opposite from the point of view of the electric field. And that means that the picture I showed earlier on with the 2 related triangular molecules is exactly the situation that we have in the holmium tungsten 10 crystal. For each molecule that gains a positive phase in response to an electric field pulse, there's a cousin that gains exactly the same but negative phase. And so when you sum all of those effects across the ensemble, what you see is no quadrature component. The out of phase components cancel, but we do see a large and oscillating in phase component. And so this graph is really a signature of a crystal with two populations of molecules that are inversion related. If we could make a crystal in which all the molecules were identical and each was inversion symmetry broken, then we would also see an oscillation in the quadrature component, the red one, just as we saw in the manganese and zinc oxide. I hope that answers the question.
This is the last one. Okay, this is maybe related to the other one. That is, should we look for the diamagnetically diluted crystals without inversion symmetry?
Should we look for diamagnetic crystals without inversion symmetry? Well, I think it's always interesting to find diamagnetic structural analogues of molecular magnets, just because then you can grow crystals where the magnetic component is a dilute subset. And then you can increase the separation between the magnetic centers and reduce the dipolar coupling, increase the phase coherence times, and do all kinds of experiments without losing orientational order. So that's the original motivation for identifying isostructural but diamagnetic versions of these molecular magnet molecules. So it's certainly interesting to do that for a wide range of reasons. Inversion symmetry or not is an important consideration when electric fields are involved. Yes.
Okay. Fernando?
Yes. Well, there have been already quite a few questions. Hello, Arzhang again. Thank you very much. So probably you are tired, but
I'm happy to take some more if there are some.
So, well, actually, a technical question. Probably I missed something. Is in this picture you have here, which is very nice. I think I understand the origin of the oscillation, but I'm not quite sure if I understand the origin of the damping and revival of the signal.
Yeah. So of course, it's quite difficult to apply an absolutely homogeneous electric field. And so across the sample, different parts of the sample are seeing different magnitude of electric field, and perhaps also a different direction. So that means that a given molecule sees an electric field that's different from a molecule elsewhere in the sample. But it's different by the same amount throughout the experiment. And so even if some molecules are rotating less fast during the first period of application, the amount by which they're rotated less is the same in the second period of evolution as it was in the first. And that's why it refocuses.
Okay.
But the fact that you get a revival is a very robust test of the fact that the effect on the spin system from the electric field is coherent.
It's coherent, yeah.
For exactly the same reason that measuring an echo is confirmation of a coherent evolution. Okay.
And you mentioned several aspects about the origin of this effect. Well, for instance, do you think that in the chromium 7 nickel and in the copper 3, the main origin is the modulation of the exchange coupling?
Yeah, that of course is the dirty secret of that experiment. We can't be certain, and there an equally good hypothesis perhaps is, for example, in the copper system hyperfine modulation, or even G-factor modulation, because each copper center has quite a anisotropic G tensor. So we actually worked with the INMA group to look at single copper centers in a comparable molecular environment as in the crystal. So we did copper zinc mixed systems. And of course, the spectrum is quite different because the exchange coupling has important consequences for the 3-spin ground state system. But we did see electric field effects in the single spin analogs. A bit different from in the triangle, but again, it's not conclusive at this point whether that tells us that the exchange modulation is unimportant, or it tells us that the G-factor anisotropy and or the hyperfine interaction are also important. And, so separating these effects is not trivial, and again, another interesting open question.
Okay, I just, David, can I make the last one? Yeah, okay. So the last one is a bit different, and I'm afraid I already put this question to you in a previous talk, so I'm sorry if it is the case.
No problem.
But, so actually you are focusing mainly on systems that have non-inversion symmetry because the effect is larger, the effect is linear in electric field, but by the same token, these systems have the drawback that many people associate with, say, electric qubits or charged qubits. While in the other case, in the system with inversion symmetry, you will have a quadratic term that somehow, with respect to the electric field, is perhaps analogous to what you have shown in the spin clock transitions. A system that is to first order insensitive. So wouldn't it be perhaps an interesting compromise to look at? So to look at systems with a slightly less control by means of the electric field, which might be, on the other hand, insensitive to fluctuations of the electric field.
So this question goes to the heart of what we're trying to do in any quantum engineering enterprise, right? So depending what we're trying to achieve, we have some objectives for the properties of the system we're designing. If we want a system that is as infinitely coherent as possible, we'll decouple it as far as possible from any environmental modulation, whether it's an intentional one or an unintentional one. But the trade-off that everybody who does anything in quantum information eventually arrives at is that systems that are controllable are sensitive to fluctuations in that control parameter. So, but this is why I mentioned that the question of the origin of an electric field sensitivity is interesting in both directions, because we might seek to design a system that is going to find itself in what we expect to be a charge fluctuating environment. And in that case, we might want to design a system to be as insensitive as possible. By the way, you're quite right to point out that an inversion symmetric system is to first order insensitive in exactly the same way as the clock transition is insensitive to magnetic field noise. But it doesn't mean that the sensitivity to larger fluctuations is small. So the coefficient of E squared can still be big.
Okay.
Right? So there are all kinds of layers to this discussion. And you're right that there isn't a single objective here. And as I said, this is what the whole game of quantum engineering is about. But anything we can learn about how structures will have properties reflecting those structures is useful in then designing systems with properties in mind. That's why the question is interesting beyond any particular system or any particular objective.
It can be a lot of fun, which is also very
absolutely, yeah, which is really the only reason.
Yeah. Okay, thank you a lot. I'm fine. Thank you.
Thank you.
Yeah, so I'm going to close the session. So thank you very much, Arzhang.
Thank you for having me. It's been a pleasure.
Yeah, I hope you have fun being the last one in this nice year in 2020. Okay.
My honor.
Okay, see you next year to everybody. Ciao.
Thank you.